All right. In this video, we'll discuss the definition of a group. We'll give plenty of examples of groups, and we'll also discuss some other important definitions relating to groups that we'll need in the next few videos. So we'll start with a non-empty set G, and we'll assume that it's equipped with a binary operation. So it's a function from G cross G to G that, in essence, allows me to combine two elements of my set and produce a new element, right? So oftentimes the operation is written as dot. So we'll say A comma B gets sent to this new element A dot B, and sometimes we'll just write AB. Sometimes we'll just juxtapose the two elements. So instead of A dot B, we'll just write AB. So this is our kind of framework. And now what is a group? So we call G a group if the operation satisfies the following rules. So first we have closure. And again, this is already implicit in our definition of the operation. But we want to make sure that if I take two elements A and B and G, then the new element I create A dot B also is inside of G. I want to make sure I have associativity. So that is for all my elements A, B, C, and G, we have A dot B dot C is equal to A dot B dot C. I want to make sure that I have an identity element. So there exists some element which is typically called E, such that A dot E is equal to A, and E dot A is equal to A. So this element is often called the identity element. It's sometimes also called the neutral element. So think of this as, if we're thinking about multiplication, this is like the number 1, where A times 1 is always equal to A, and 1 times A is always equal to A. So this is our identity element. And then finally, we have inverses, so that if A is an element of my group, then there exists some other element B, such that A dot B gets me back to my identity, and B dot A gets me back to my identity. So under my operation, all my elements are invertible. Okay, so this is the definition of a group. It's these 4 axioms. It's much simpler than a ring. There's less stuff going on here, mostly because we only have one operation to worry about. You might ask, well, what about commutativity? Well, a group that is commutative, you can probably guess it's called an abelian group. So we'll call a group abelian if for all A and B and G, we have A dot B is equal to B dot A. So these are some of our basic definitions. So just a few quick definitions. We'll call G a finite group if the cardinality of G is finite. So if G is a set with finitely many elements in it. In this case, we'll say that G has finite order. We're going to see that we're going to encounter a lot of finite groups more often than we encounter finite rings. So if G has finitely many elements, we'll say that G has finite order, or we'll just call G a finite group. If the order of G, or the cardinality of G, is not finite, we'll say that G has infinite order, right? So if G is an infinite set, we'll say that G is a group of infinite order. So now we can finally move on to examples of groups. So our first example is going to be very familiar. It's that any ring under addition, if we forget about the multiplication operation and just consider the ring under addition, becomes an abelian group. So let's check this. So in order to check this, all we have to do is make sure that all the axioms of a group hold. And all I'm going to do is rewrite the axioms of addition from the ring. So we have closure for all A and B and R. We had A plus B was an R. So this was one of our ring axioms. We had associativity. This was another ring axiom that addition was associative, that A plus B plus C was the same as A plus B plus C. We have identity. In this case, the identity is that 0 element, right? So recall that our E is going to be 0, and we have that 0 plus A is equal to A, and A plus 0 is equal to A. So here our operation is addition. So instead of juxtaposing or writing a dot, we're writing plus, because this is our operation. So we have an identity. We also had inverses. For every A and R, we showed that the additive inverse of A was an R. We called it negative A because we proved that it was unique. And in particular, we know that A plus its additive inverse is the identity 0. And the inverse of A plus A is equal to 0. So this is again following from our ring examples from earlier, or from our ring axioms. And then finally, we know that this is abelian because one of our ring axioms was that addition was commutative, namely that for all A and B and R, that A plus B was equal to B plus A. So a natural question to now ask is, well, what about the multiplication operation? Does a ring become a group if I only consider multiplication? And the answer is no. A ring will actually never be a group under multiplication. So in this example, I'll consider a ring with identity, because this is going to be our E element. So the question is why, right? So in this example, E is going to be 1R, since I know that for all A in my ring, A times 1R is equal to A, and 1R times A is equal to A, right? So this is our E element, but we also know that for all A in my ring, A times 0, we proved was always equal to 0. So it's impossible to find an inverse for 0, to find a B and R such that B times 0R is equal to 1. That is, unless 1 is equal to 0, in which case your ring is just a 0 element anyway. Okay, so this is impossible. So under multiplication, a ring is never a group. A ring with identity is never a group. So at this point, you might ask, well, is there any part of the ring that we can salvage and still get a group under multiplication? So the answer to this question is yes. Actually, if we take a certain subset of our ring, so we'll define U of R to be all the elements A and R such that A is a unit, it'll turn out that U of R is actually a group under multiplication. And again, we have to have a ring with identity if we want to talk about units in the first place. Okay, so let's prove this. Well, first we'll look at closure. I'll say, suppose U and V are in U of R. So that means U and V are units in R, which means that they're invertible. So this tells me that U inverse and V inverse are elements of R, and that U times U inverse is 1, and U inverse times U is 1. And similarly, V times V inverse is 1, and V inverse times V is 1. Our goal is to now find an inverse for UV. So our goal is to show that UV is a unit. So how do we do that? Well, we're going to use V inverse and U inverse to construct the inverse for UV. So what do we have? If I take UV times V inverse U inverse, I'm going to get 1. Why? Because V times V inverse is 1, so I'll end up with U times 1 times U inverse, which is just U times U inverse, which just gives me back 1. And then similarly, if we swap them, V inverse U inverse times UV is also equal to 1. Why? Because U inverse times U is 1, so we end up with V inverse times 1 times V, which is just V inverse times V, which leaves me with 1. Okay, so from this, I get closure. I've shown that UV is also a unit. I found the multiplicative inverse for UV. So this gives me closure. Again, I wanted to show that if U and V have multiplicative inverses, then so does U times V. So I've done that. The other axioms are actually pretty straightforward. This was kind of the hard part of this check. Associativity, well, we're just looking at a subset of R, and we already know that multiplication in a ring is associative. So U of R just inherits associativity from R. We know that the identity element itself is in U of R, since 1 times 1 is equal to 1 inside any ring. So this is our E element, this is our neutral element. And then finally, inverses. Well, if U is a unit, what does that mean? That means U times U inverse is 1, and U inverse times U is equal to 1. But what does that tell me? That tells me that U inverse is invertible, and its inverse is U, right? So I end up with U inverse is an element of U of R as well. Okay, so this is a group. It's going to be called the group of units of a ring, and I'd like to look at some interesting examples of this group. So let's look at some examples of groups of units of a ring. So U of R, we're going to refer to as the group of units of R. Okay, so what are some examples? Well, the first type of ring we'll consider is a field. So if F is a field, we know that all of its non-zero elements are units. That's by definition of field. So U of F is just going to be F minus 0. We're going to remove the 0 element. And typically this isn't called U of F. It's typically called F star. So if you have a field and removing 0 from it gives us a set called F star, which is a group under multiplication. And in fact, it's an abelian group because we know that the multiplication in a field is commutative. Remember, fields are commutative rings with identity where every non-zero element is a unit. Okay, so F star is an abelian group. So what are some examples of groups that we get here? Well, we get that R star, so the reals without 0, are a abelian group under multiplication. The non-zero complex numbers, the non-zero rational numbers, these are both abelian groups under multiplication. Z mod P with the 0 element removed is an abelian group under multiplication. And so we've just produced a whole bunch of interesting groups under multiplication here. So another interesting group of units would be the group of units of Z mod N in general. So for example, in Z mod 8, the units are the relatively prime elements of the elements relatively prime to 8. So Another interesting example is the group of units of, let's say, Z mod 8. We can do this for any Z mod n. So these are the elements in Z mod 8 that are invertible under multiplication, and these are 1, 3, 5, and 7. And we proved earlier that these are precisely the elements that are relatively prime to 8. So this is a group under multiplication. So we can actually write out a multiplication table, or what's called a Cayley table, for this group, and we get something that looks like this, right? 1 times anything is itself, so 1 times 1 is 1, 1 times 3 is 3, so on and so forth. We can also check that 3 times 3 is 9, which in Z mod 8 is equivalent to 1. We know, for example, 3 times 5 is 15, which in Z mod 8 is equivalent to 7, and so on and so forth. And we get this abelian group structure. In general, U of Z mod n is just going to be the equivalence classes of K, where K is some integer bigger than or equal to 0 and less than n that's relatively prime to n, right? So that's what we've done here. So in this case, we have n is equal to 8, and the k's that we can choose are 1, 3, 5, and 7. The other thing I'll point out here is you might ask, what's the order of Z mod n? This is actually something called the totient function. So the order of Z mod n is defined to be phi of n, and phi of n is something from number theory called Euler's totient function. So another interesting example of this is the group, it's called GL2 of F. And GL2 of F is called the general linear group. And this is the group of units of M2 of F. So we're going to take all the 2 by 2 matrices whose entries, A, B, C, and D, come from F, whose determinant is non-zero. So these are the invertible matrices, the invertible 2 by 2 matrices. The theorem above, or the example above, tells us that this is a group under matrix multiplication. And more generally, we don't have to work with 2 by 2 matrices. In general, we can talk about invertible n by n matrices, and this gives us what's called the general linear group. So here's an example of something that's also not a group. So we're going to consider Z mod 8, and we're going to remove the 0 element, and we'll show that this is not a group under multiplication, right? One of the reasons a ring was not a group under multiplication was that the 0 element couldn't be inverted. So now we can ask this question of, well, what if we remove the 0 element? What ends up happening? Well, we'll see that we run into some problems pretty quickly. So the first thing we'll note is that the identity element, if this is going to be a group, it has to be 1. If I'm using multiplication, I know that A times 1 is equal to A, and A is equal to 1 times A for all elements A in this set. So the next question I can ask is, well, what about an element like 2? Does 2 have an inverse? And the answer is actually no, 2 does not have an inverse, and we'll run into some problems. So the first thing we'll notice is that 2 times 1 is equal to 2. 2 times 2 is equal to 4. 2 times 3 is equal to 6. 2 times 4 is equal to 0, so I can see right there that I've lost closure, right? I'm multiplying 2 elements inside the set and getting something outside of my set. 2 times 5 is equal to 2. 2 times 6 is equal to 4. And 2 times 7 is equal to 6. So I see right away that there's nothing I can multiply against 2 to give me back 1. And I see that 2 times 4 lands me outside of my group, or outside of my set, rather. It's not a group. So it lands me outside of Z8 minus 0 because I end up with 0. Okay, so Z8 minus 0 is not a group under multiplication. And here the main obstruction is the fact that we have 0 divisors. And finally, the last thing I'd like to point out is that 0 divisors aren't always the obstruction. So for example, let's consider the integers where I've removed 0. This is also not a group under multiplication. So similar to above, we have that 1 is going to be our E element. 1 is our neutral element because 1 times any integer is just the same integer. And we can also say that here 2 also has no inverse. If I want to find an inverse of 2, I want to find something to multiply against 2 to give me back 1. Well, there is no integer solution B to this equation. So I see that 2 is not invertible, even though Z has no 0 divisors. So I see that Z minus 0 is not a group under multiplication. Another class of groups that's really interesting is what are called the dihedral groups. So we're going to start by studying the symmetries of a triangle. So we're going to start with an equilateral triangle, and we're going to ask, what kind of operations can I perform that give me the same triangle back, but might permute the corners? So the 1, 2, and 3 might get permuted somehow. So the first operation I can do kind of is natural. I could just do nothing to the triangle. I could do what's called a 0-degree rotation. So that takes my triangle and leaves it unchanged. Another thing I can do is I can rotate the triangle counterclockwise by 120 degrees. So I could take this triangle and just rotate it 120 degrees. So when I do that, what ends up happening is, again, I'm rotating this way by 120 degrees. So my 3 ends up down here, my 1 ends up over here, and my 2 ends up here, right? So I have this arrangement of my corners. Another symmetry I have is a 240-degree rotation. So I could take this and rotate it by 240 degrees. In this case, 3 is going to get rotated over here, 2 gets rotated down here, and 1 gets rotated this way. So again, this is a counterclockwise 240-degree rotation. Okay, so this is another symmetry. And then you might ask, well, what about reflections? Can I reflect my triangle? So the answer is going to be yes. So the first reflection I can do is a vertical reflection. And what does this amount to? This amounts to just swapping the 1 and the 2, right? So I'll leave the 3 fixed and I'll swap the 1 and the 2 with one another, so that here I have the 3 on top and I have a 2 and a 1. Another symmetry might be a reflection along one of the diagonals. So I have a symmetry along this diagonal, and what that's going to amount to is leaving the 1 in place and swapping the 2 and the 3. So I'll do that, and I have the following triangle. And then finally, you might say, oh, well, there should be one more. There's the reflection along the other diagonal, and you'd be right. So if I reflect along the other diagonal, I'm going to end up swapping the 1 and the 3. And I'm going to call this symmetry D2. And so I get the same triangle, but I've swapped the 1 and the 3. So this is an important set. This is actually called D3, and these are the symmetries of an equilateral triangle. So it's going to be the 3 rotations and the 3 reflections. At this point, you might be asking, well, how is this related to group theory? So let's try to perform some of these operations in sequence. So I'll start with this triangle 1, 2, 3 in its normal orientation. And what I'm going to do is I'm going to apply the operation D2 first. So if I apply D2, I'm going to leave the 2 fixed, and I'm going to swap the 1 and the 3. And now what I'm going to do is I'm going to take this triangle and apply the operation D1 to it. So I'm going to leave the 3 fixed, and I'm going to swap the 2 and the 1. So when I do that, I get the following triangle. I get 3, 1, 2. So the question you might ask is, well, is there a way to get from that first triangle to that third triangle? Is there any operation we've done that gets us from the first one to the third one? If we look at our operations, we see that that's actually a 120-degree rotation. So this tells me that combining the 2 reflections, doing D2 first and D1 second, is the same as just rotating by 120 degrees. So I'm writing this as function composition where I'm reading it from right to left. So we apply D2 first and we apply D1 second. And that gives us the same result as 120. Another thing to try is if you apply them in the other order, if you do D1 first and then D2 second, you'll get a 240-degree rotation. So we can try this for others. We can say, well, what if I take this triangle and first rotate it by 120 degrees counterclockwise, and then apply the symmetry V? What do I end up getting? Well, I end up with the following triangle. V, remember, it flips the 1 and the 3 down here, and it's going to leave this 2 up here fixed. So I end up with this triangle, and then we can ask again, well, what does this get me? If how can I get from the first triangle to the third triangle? I might notice that this is the same as just doing D1 to my original triangle. And so now I have this operation that V times R20 is equal to D1. And I can do this for all of my operations. And what I'll see is that I actually have the structure of a group. Another thing that might be interesting to check is that R120 times V, if we do it in the reverse order, so we apply V first and then do R120, we'll actually end up with D2. So this is going to be a group, but it's not going to be commutative, right? So if we did this in the reverse order, up here we would get something like D2, D1 is R240, and R120V is equal to D2 if we tried this out. So we'll see that this group is not abelian. So using this operation, D3 is going to become a group, and its identity element is just a 0-degree rotation. So anything composed with a 0-degree rotation is just itself. So if I do a vertical reflection and then apply a 0-degree rotation, that's the same as just doing a vertical reflection. So I'll get R0 times V is equal to V. And the same for all the other elements. So a little note about inverses, however, note that R0 times R0 is R0. So if I do a 0-degree rotation and then another 0-degree rotation, that's the same as just doing a 0-degree rotation. R120 times R240 is a 360-degree rotation, which is the same as a 0-degree rotation. So R120 times R240 gets us back to where we started, as well as R240 times R120. We'll note that the vertical reflection is self-inverting. So v times v is r0. So if I apply v and I apply v again, I get back to where I started. Same thing with d1 and same thing with d2. So it turns out this idea applies to any regular polygon. So we could do this for a square, a regular pentagon, a regular hexagon, so on and so forth. And we'll call dn the symmetries of a regular n-gon. So dn is going to contain n rotations and n reflections. And one thing I'll point out is some sources call this a group d2n to indicate that there are two n elements in it, and some sources will call it a dn to indicate that it's the symmetries of an n-gon. So if you're reading about this in other sources, be careful about which name is being used. So let's look really quickly at the symmetries of a square. One thing I might notice with a square is I have 4 rotations. I have a 0-degree rotation, a 90-degree rotation, a 180-degree rotation, and a 270-degree rotation. So those are 4 elements of D4. Those are my rotations. And then I have 4 reflections. So I have this reflection, which I'll call V. So this will be a vertical reflection. I have another reflection, a horizontal reflection, I'll call H. So this will be my element H. I have a diagonal reflection going this way. So I'll call this guy D1. And then finally, I have a diagonal reflection going the other way. So I'll call this element D2. So these elements together form the set which we'll call D4. So these are the symmetries of a square. And then I could repeat this for a pentagon. I'll get 10 symmetries. I can do this for a hexagon. I'll get 12 symmetries, so on and so forth. So these are what are called the dihedral groups. And I've taken the time to kind of write that at the bottom. It's called a dihedral group if you'd like to learn more about them. The last type of group we're going to study is a group of permutations. So what is a permutation? So typically when we think of a permutation of, let's say, the numbers 1 through n, we typically think of it as some sort of rearrangement or reordering of the numbers. So for example, 2, 3, 1, 4 would be a permutation of the numbers 1, 2, 3, 4. So this is kind of the common way we think about permutations. And what I'd like to do is to kind of give this another definition. So we're going to think of permutations as functions. So we'll represent a permutation as a bijection. So in this case, if I want to do, for example, the set 1, 2, 3, 4, I want to represent a permutation of the numbers 1, 2, 3, and 4. It'll be a bijection from the set containing 1, 2, 3, 4 to the set containing 1, 2, 3, 4. So let's think about our permutation up here. How can I represent that as a bijection? So what I'm going to do is the following. I'm going to say the permutation above is f of 1 is 2. I'm indicating that the first element is 2. F of 2 is 3. So I'm indicating that the second element is 3. F of 3 is 1. So I'm indicating that the third element is 1. And f of 4 is equal to 4. So I'm indicating that the fourth element in my permutation is 4. So this bijection represents our permutation. So how can I write this a little bit more cleanly? I'm going to write it in the following way. So I'm going to express the function where the top row is my domain, the top row is my 1, 2, 3, 4, and the bottom is telling me where these numbers are being mapped to. So this is telling me that f of 1 is equal to 2, f of 2 is equal to 3, f of 3 is equal to 1, and f of 4 is equal to 4. So I'm going to represent my bijections this way. And we could see pretty nicely that this permutation 2, 3, 1, 4 appears as the bottom row of this bijection. Okay, so one thing I know now is I know how to compose functions. So I might say, okay, if I want to compose 2 permutations and get a new permutation, all I have to do is compose these 2 functions. One thing that's true is that if I compose 2 bijections, I get a new bijection. So let's work on composing f and g together. So what is f composed with a g? So I've written f over here, I've written g over here, and we're going to plug elements one by one in. Right, so remember, I'm going to take 1, I'm going to plug it into G, and I'm going to get 4. And then I'm going to take that 4 and plug it into F, and that's going to give back a 4. So I see that in the end, 1 gets mapped to 4. I'm going to now ask, where does 2 go? Well, 2 goes to 3, so G takes 2 and maps it to 3. And now I have to take that 3 and plug it back into F. So what is F going to do? F is going to take 3 and map it down to 1. So in the end, 2 goes to 1. I can ask myself, where does 3 go? Well, G maps 3 to 2. And what does F do? F takes that 2 and maps it back down to 3. So 3 ends up going to 3. And then finally, where does 4 go? 4 goes down to 1. And then 1, f sends 1 to 2. So in the end, 4 gets sent to 2. And I've written down this new bijection. So the composition of these two permutations, f composed with g, is this new permutation 4, 1, 3, 2. So I can now ask the question, well, what if I want to compose them in the other order? What if I want to apply f first and then g second? So let's see what happens. So first, let's look at what happens to 1. F of 1 is 2, and then I have to take that 2 and plug it into g. So g of 2 gives me back 3. So in the end, I see that 1 gets sent to 3. Well, what comes next? 2. 2 gets mapped to 3, so f of 2 is 3. And now I have to take that 3 and plug it into g. So I see that 3 gets mapped back down to 2. So 2 gets sent to 2 in the end. So I'm only looking at what is my starting point and what is my ending point. What does 3 do? 3 gets sent to 1, and then 1 gets sent down to 4. So I finish at 4. So 3 gets sent to 4. And then what does 4 do? 4 gets sent to 4, and then this 4 gets sent down to 1. So in the end, 4 gets sent to 1. So I have the following permutation. So one thing I notice right away is that f of g does not equal g of f. Okay, so that's one thing that I noticed right away. So whatever structure I'm forming here is not going to be commutative. So in general, we're building up to a group structure, and we'll see that this is not going to be a commutative group or an abelian group. So it turns out it's pretty easy to identify the identity element. The identity element E is going to be the map that just sends every integer to itself. So 1 goes to 1, 2 goes to 2, 3 goes to 3, and 4 goes to 4. So just to check that this works, let's do a test on this element right here that we've been working with, f. So I'm going to do E composed with f. And let's try to do this. So if I want to do E composed with f, where does 1 go? Well, f sends 1 to 2, and then E sends 2 back to 2. So I'm going to get 1 goes to 2. Where does 2 go? F sends 2 to 3, and then E sends 3 to 3. So in the end, 2 goes to 3. Where does 3 go? F sends 3 to 1, and E sends 1 down to 1. So 3 goes to 1. And then finally, where does 4 go? Well, F sends 4 to 4, and then E sends 4 to 4. So 4 just gets sent to 4. And I see that I get F back. And I could do similarly. I can say that F composed with E is equal to F, right? And this works for all permutations. So in general, this is true for all permutations. Okay, so that's how I can get the identity. And now the question is, how do I get inverses? Well, it turns out that inverse functions are going to give us the inverses. So let's think about how to write down the inverse function of f. So I'm going to notice the following. I'm going to notice that f sends 1 to 2. F of 1 is equal to 2. So what is f inverse going to do? F inverse is going to send 2 to 1. So I'm going to fill in the 1 there. I notice that f sends 2 to 3. So f inverse is going to go backwards. F inverse is going to send 3 to 2. I notice that f sends 3 to 1. So f inverse is going to go backwards. F inverse is going to send 1 to 3. And then finally, I notice that f sends 4 to 4. So f inverse is going to send 4 to 4. So this is my inverse. And now I can check, does this actually work? What happens when I compose these two? Well, let's see what happens. I'm going to notice, well, where does 1 go? F inverse sends 1 to 3, and then f sends 3 down to 1. So I end up going from 1 to 1. F inverse sends 2 to 1, and then f sends 1 back down to 2. So I end up going from 2 to 2. F inverse sends 3 to 2, and then f sends 2 back down to 3. So I end up sending 3 to 3. And then finally, I end up sending 4 back down to 4. So I get the identity. And I could say similarly, f inverse composed with f is also equal to my identity. Okay, so now the thing you might be noticing at this point is that we have a group structure. So let's kind of summarize our findings. Okay, so now we're finally ready to address what's actually going on here. And for this proof and these ideas, we're going to assume some basic facts about functions that are typically covered in a proof writing class. So we'll let A be the set of elements 1 through n, and I'll define Sn to be all the functions from A to A, which are bijections. So these are all the permutations from A to A. And so the theorem we have is that the set Sn is a group under function composition. So let's prove this. So for closure, we're just going to use the fact that the composition of two bijections is a bijection. So if I compose two bijections, I get a bijection. So the composition of any two functions in Sn is going to be an element of Sn. Associativity, we just use the fact that function composition is associative. Identity, well, we have this identity element, E, which maps every element of A to itself, right? So E of A is equal to A for all A in capital A. This is my identity function. So let's check this. I know that E of F composed with A is just E of F of A. And now I know F of A is an element of A. So E of this element of A is just that element of A, which is F of A. So I get that E of F is equal to F. And similarly, the other way, F of E of A is F of E of A. And I know that E of A is equal to A, so I just end up with F of A. So this tells me that F composed with E is also equal to F. So I see that E is the identity. And then finally, for inverses, I just use the fact that if F is a bijection, its inverse is also a bijection. And in particular, F of F inverse is equal to E, and F inverse of F is equal to E. Okay, so this is just using basic facts about functions to show that this group, that this structure is a group. Okay, and finally, I just want to point out that Sn is often just called the symmetric group on n symbols. So it's just all the permutations of n distinct objects. In this case, we just call their objects 1, 2, 3, 4, all the way up to n. So this is called the symmetric group on n symbols, or n elements, or sometimes just simply the symmetric group. The question you might ask is, well, what's so special about using the set A having n symbols, right? What's so special about A being finite? Well, it turns out nothing. It turns out this construction and this proof works in general. So in general, if A is any set, then we can define sim of A. So these are, again, all the functions f from A to A, such that f is a bijection. And this is going to be a group under function composition as well. And this will be called the symmetric group of A. So this can be an infinite set. It can be a countably infinite set, an uncountably infinite set. It could be anything. And so the sim of A is, in some sense, a generalization of the notion of permutations of that set. We'll talk a lot more about the symmetric group in future videos. So right now, I just wanted to kind of introduce it as an example of a group, but I'm planning in the future on doing a whole video on the symmetric group and properties of the symmetric group.